Today we are going to look into these microemulsions, whereby microemulsions are thermodynamically stable dispersion. It is different from the emulsion that we have studied before. However, it is still involves the components of oil, water, and surfactant in the formulations of microemulsions. Microemulsions, it has the size of around 1,100 angstrom, and which is 100 times smaller than the typical emulsion droplet size. This image shows the appearance of microemulsions and also the emulsion. The appearance of microemulsions is similar to something that is transparent, or we call it as the translucent. The preparations method of microemulsions involve dissolve the surfactant in oil, followed by additions of water, and then we just shake the mixture to give us the product, which is something similar to this. The stability of microemulsion stems from the interplay of interfacial tension and also the free energy. Meaning that the free energy will determine the stability of the microemulsion, and it will involve the parameters such as the change of surface area, the interfacial tension between the oil and also the aqueous medium, as well as the change of entropy. So the delta G is also depends on the temperature of the microemulsions, where it is prepared and also stored. The increase in the interfacial tension between the phases cause the change in the stability for the microemulsion. In the preparations of microemulsions, we are going to produce a lot of the small size droplets, which it will enhance or increase the surface area compared to the conditions before we produce the small size droplets. So it will result in a very huge change in the surface area before and after the productions of microemulsions. This will result in the value of delta G become a very much positive value. Although the delta S is related to the entropy of the system, where by the formations of microemulsions, the entropy of the system will increase because more droplets will be formed. However, the increase of this delta S is insufficiently to overcome the change of the surface area, which eventually results in a delta G value with positive value. Therefore, one of the ways in order to change the delta G is either by minimize the delta A or change the interfacial tension. So if the delta G is equals to negative, then we will be able to get a spontaneous formation system. Therefore, it is much better to change the interfacial tension compared to minimize the delta A. So how to change the interfacial tension? One of the ways that we can do is that we have to use additional surfactant, which is named as pore surfactant in the formulations, in order to further reduce the interfacial tension to a value which is close to zero. So if interfacial tension equals to zero, meaning that the whole expression here will become a negative value. Therefore, we will achieve a system which can be formed spontaneously. If we use the ionic type of surfactant, such as sodium disulfide, then we will repeat the pore surfactant to reduce further the interfacial tension. The example of the arrangement for this SDS in the aqueous phase is something similar to the figure given here. So SDS will arrange at the interface between the oil phase and also the water phase. If we do not have the core surfactant, okay, as the structure given here with the green color, then we can only achieve the interfacial tension, which is still remain high, although the CMC has already reached. Meaning that at the point where the SDS form the micelles, the interfacial tension is still with a very high value. Therefore, in order to further reduce the interfacial tension, after the SDS achieve the CMC, what we can do is that we add another type of surfactant into the mixture. So this surfactant, it can be arranged at the interface and occupy those space in between the SDS molecule. With that, with the presence of this core surfactant, the interfacial tension can be further reduced. And this will be benefiting the delta G value to become negative. However, if we use other type of the surfactant, for example, surfactant with double chain, such as the aerosol OT, which is to this structure, aerosol OT, which is the sodium beta hexyl sulfur succinate. It has an anionic group pattern for the head half, and it possesses two hydrocarbonic tail. So this structure is arranged in the negative curvature shape, which is similar to this arrangement, whereby there has the tail to be pointed to the outer layer, to the medium, and the head group will be pointed one to another at the inner part, which is something similar to the reverse micelle, due to the very large hydrocarbon tail. So it might not tend to form the normal micelle. And eventually we get the reverse type of micelle to be formed, which consists of this negative curvature shape. And this kind of this kind of molecule, it has the ideal packing shape for the water in oil type emulsion dimensions. So generally, we only need to have the aerosol OT to be included in the formulations of microemulsions, where it did not require the additions of core surfactant in order to further reduce the interfacial tension. Means the type of the surfactant will determine whether the additional surfactant, which is the core surfactant, is required in the formations of microemulsions or not. So what are the characteristics of microemulsion? Microemulsions are thermodynamically stable because it has the delta G value of negative equals to 0. The interfacial tension between the phases, water and oil, or the aqueous or the oil phase, is very low. It is ultra low in the region, in the value of 1 micronewton per meter. And it can be formed spontaneously without applying any of the external forces, like when we need to prepare emulsions. The size of the microemulsions is in between 1 to 50 nanometer, and it contains a very large oil and water interface area. The delta A is a very large value. This one, the appearance of the microemulsions is transparent due to the very small size, and they are kinetically unstable. There are two types of microemulsions. Microemulsions can appear as a droplet types, like emulsions. So it is either spherical oil droplets dispersed in the continuous medium of water, refers the oil in water microemulsions, or it forms the spherical water droplet dispersed in the continuous medium of oil. And dissolve in the water in oil microemulsion. Microemulsion also form the random biocontinuous mixture or the lamellar mixture. This type of structure is different from the emulsion. So the biocontinuous structure in microemulsions was proposed by these people. It is something similar to a sponge where they have the interconnected three dimensions in the center of the particle, of the droplets. So it is an important structure in the microemulsion system. The case study will help to elucidate the different cases which exist. And the different phases their existence will depend on the composition ratio of the ingredient. Besides, these microemulsions will also, their traces will also interchange between one to another. One of the unique factors associated with the microemulsions is the different structures as classified by Windsor. There are 4 different types of microemulsions, which are Windsor 1, Windsor 2, Windsor 3, and Windsor 4. Windsor type 1 microemulsions, it has the 2 phases, same as the Windsor 2 microemulsions, also has 2 phases. So type 1 is the consists of the surfactant is preferentially soluble in water, and it will form oil in water microemulsion, whereby it also consists of the surfactant-rich water phase coexist with the oil phase, shown in this figure here. Therefore, you have the top layer, which is the excess of the oil phase, and then the bottom here, it has the oil phase dispersed in the water phase. For Windsor 2 type, two microemulsions, it has the excess of water phase. And then on top of the it is the microemulsions with the water dispersed in the oil phase. So this is known as the type 2 microemulsions according to Windsor. Whereby type 2 microemulsion is different from the type 1 and also type 2. Type 2 microemulsions, it has 3 phases, phase 1, phase 2, and also phase 3. So it has the surfactant-rich middle phase coexist with this both excess water and also oil, which these 2 phases has a less surfactant, or we call it as poor surfactant phases. And this middle phase, they don't form the droplet types of the microemulsions, but biocontinuous phase is one of the possible structure of these middle phase microemulsions. While type 4 microemulsions is the single phase, or we call it as the isotropic micellar solutions. It will be formed upon additions of sufficient quantity of the surfactant plus some co-surfactant. Windsor 4 has only consists of single phase. Shows the appearance of the different types of microemulsions according to Windsor. We have the 2 phases microemulsions, which is the water in oil type, and also the oil in water type microemulsions. And by the middle one, it has the 3 phases. The middle part here, the middle phase is the biocontinuous phase. So this one we will have the microemulsions with the excess of the oil phase, water phase. And this one is oil in water microemulsions with excess of oil phase. So in fact, these 3 phases, it will change It can be transit from one to another. So transition from a two-phase system involving an oil-water droplet type microemulsions to a two-phase system involving a water in an oil droplet type, meaning that if they want to reverse the phase, so for the transitions from the oil in water microemulsions to water in oil microemulsions, it needs to pass through the three-phase system before they end at the water in oil microemulsion system from oil in water microemulsion system. So these phase transitions can be realized in many different ways. We can change the phase by increase the concentrations or by adding in the electrolytes when the surfactant is that we use is the ionic type of surfactant, or we can also change the temperature of the system, especially when we use the non-ionic type of surfactant. So it will change the hydrophobicity of the surfactant and results in the transitions phase to occur. Surfactant that we use is a kind of an ionic surfactant. When we add in the electrolytes, such as we add in some salt into the medium, it will cause the phase transitions from oil and water emulsions to water in oil emulsions. For these transitions, before it can achieve the water in oil microemulsions, it has to go through this phase. Similarly, if we use the non-ionic surfactant, then it will also be transit from oil in water microemulsions. It will increase the temperature. Okay? The temperature will cause the dehydration of the heat group for this non-ionic surfactant and cause the surfactant to become more soluble in oil. Therefore, it will transit the phase from oil in water to water in oil type microemulsions. And similarly, it will go through this phase before achieve the water in oil microemulsion system, which is the type 3 microemulsion. To explain the influence of this surfactant and also the solvent on the interfacial curvature, R ratio was applied. Okay? So the R ratio is one of the characterization concept where it was proposed by Winsor to explain the influence of amplifiers and also solvents on the interfacial curvature. The primary concept is to relate the energies of interaction between the amplifier layer with the oil and with the water region. Therefore, the R ratio compares the tendency for an amplifier to disperse in the oil and also to its tendency to dissolve in the water. If one phase is much more favorable for the surfactant, then the interfacial region that tends to keep on and definite curvature. So let's look into what are involved in this R ratio. The interaction energy at the interface region of an oil, surfactant, and also water system. Given that in the microemulsion system, okay, there are three distinct regions that we can categorize it, such as this region, which in this diagram here, it is represented by this alphabet W. And then we also have the oil region here, represented by the symbol of O, as well as the anti-fluid region, which is represented by the surfactant region. It consists of the head and also the tail part. The cohesive energy between molecule X and Y is defined as AXY. So AX1 equals to cohesive energy per unit area between molecule X and Y. If this value is positive, it indicates that the interactions between the molecules are at their time of effective interactions. So there are different kinds of interactions can occur between if you have the surfactant molecule dispersed in or consists of water. So what are the interactions that are involved? We have the surfactant molecule dispersed in water. Okay? So here is the water phase, while this one is the oil phase. Alright. Basically, heat group will be facing the water phase, and the tail will be facing the oil phase. And this zigzag it represents the structure of the oil with the hydrocarbon. The heat group of the surfactant will interact with the water phase. So we have the A, H, C, and D, which indicate that the cohesive energy between the heat group of the surfactant molecule with the water molecule. In addition to that, the heat group will also interact with another heat group from another surfactant molecule. So it results in this AHH. Now, other than these two interactions which can occur in the aqueous phase, the surfactant molecule may also have some interactions with the oil phase. Therefore, we have the AHCO. So, in addition to these heat group interactions with water and also oil, the third part from the surfactant molecule will also interact with the oil phase and also the water phase. Therefore, it results in the different kind of intermolecular interactions and also the cohesive force that will occur when we have the surfactant dispersed in water and also oil. We consider the cohesive energy that is occur in a surfactant molecule. So it can be represented as ACO, or the interactions between the surfactant and also the oil phase. So what will contribute to this cohesive energy? It will involve the cohesive energy for the surfactant part, which is with the hydrophobic part, the tail part, interact with the oil phase. So in addition to that, we also have the interactions of the surfactant molecule heat group with the oil phase. So this will characterize the interactions for surfactant with the oil phase. For the interactions of the surfactant with the water phase, it involves the tail part from the surfactant interact with the water, as well as the heat group of the surfactant interact with the water phase. So these two types of interactions result in the surfactant interactions interact with the water phase. But if you look into these interactions between the heat group and heat group of the surfactant with the oil phase, as well as the flow part of the surfactant with the water phase. In fact, these two values are very small, so we can ignore these two values. In other words, the cohesive energy contribute to the surfactant in this system, as well as it consists of water and oil, is mainly come from the interactions between the surfactant tail with the oil part. While The cohesive energy in the water phase contributed by the surfactant molecule is mainly come from the cohesive energy between the surfactant molecule of the head group, okay, interact with the water phase. Shown just now, other than the interactions between the surfactant and with the oil phase or the water phase, there will also involve other interactions such as the water-water, oil and oil interactions, the interactions between the hydrophobic parts from the surfactant molecule, as well as the interactions between the hydrophilic parts from the surfactant molecule. So the interactions between the oil and also the hydrophobic part, they will unlikely to be interact with the water phase. Similarly, those cohesive forces which involve the water phase is also opposed to the miscibility with the oil phase. And if the interfacial stability, okay, can be achieved, it can be predicted from the difference in the surfactant interactions between the oil and also the bulk phase. If this value, the difference between the surfactant interactions in the oil and also the water bulk phase is very small value, it indicates that the microemulsions that will be formed is it can achieve a much stable interfacial stability can be achieved. Insert express qualitatively these variations in dispersing the tendency by using the R ratio, which involves the ratio between the cohesive energy for the surfactant in the oil phase to the cohesive energy for the surfactant in the water phase. To account for the structure of the oil phase and the interactions between the surfactant molecule, there are derived and extended versions of the original R ratio, which is given here. So, the initial primary concept is that the R ratio of the cohesive energy arising from the interactions of the interfacial layer with oil divided by the energies resulting from the interactions with water determine the preferred interfacial temperatures. If R is greater than 1, the interface tends to increase its area of contact with water with oil, or decreasing its area in contact with water. Therefore, oil tends to become the continuous phase, and the formations of microemulsion corresponding to type 2, just the Binzer 2, will be found. Similarly, the balanced interfacial layer is represented by R equals to 1. So that is one of the ways to predict which type of the microemulsions will be found according to the cohesive energy which are involved in between the surfactant and the oil as well as the water phase. In this table, it lists down the comparison between the microemulsions and also the emulsion. Basically, emulsion is thermodynamically not stable, but microemulsion is thermodynamically stable. Microemulsions will require the additions of co-surfactant in order to minimize the interfacial tension between the water and also the oil phase. While emulsion does not require the addition of co-surfactant in the formations of emulsions, the droplet size of the dispersed phase in emulsion is very large compared to the microemulsions. The appearance of the emulsion is whitish, but microemulsions appear as transparent dispersion. In order to prepare emulsions, it requires intense agitations. But for the preparations of microemulsions, we just need to mix the oil, water, and surfactant as well as four surfactants, and just gently shake it, and we will get the microemulsions. With that, I end the topic of microemulsions.